Welcome. Today we are discussing Module 5.2, Writing a Document Loader and Splitter, Practical. Here is a quick look at where we are in our curriculum. Welcome back, engineers. In this practical module, we are diving deep into building a production-grade document loader and splitter from scratch. Most AI developers treat data loading as an afterthought, relying on generic utilities that blindly chop text, leading to catastrophic context degradation inside vector stores. Today, we will examine how proper, deterministic text pipeline engineering prevents this issue completely. We'll start by exploring the end-to-end architecture flow to show you how clean text flows from static files into highly metadata-enriched, search-ready chunks. Let's design a pipeline that maintains absolute semantic boundaries and structured context. To understand how this operates under the hood, I will show you how to write a dedicated document loader class in Python. This implementation uses explicit file operations and injects critical document-level metadata, ensuring our system remains transparent. Please check the link in the description to download the architecture diagram and script so you can follow along on your machine. I'm focusing on strict type hinting and robust exception handling here because, in a real production server, unhandled edge case files will halt your entire ingestion pipeline. Notice how we calculate metrics like character and word counts on the fly to append to our metadata payloads. Now, let's look at what happens when we execute this custom loader inside our test environment. I will run the Python script to read a sample enterprise policy document. As you can see from the simulated console logs, the file loader executes instantly, producing clean metadata. It correctly flags the source document, identifies the total characters, and measures structural statistics. This absolute predictability ensures that downstream embedding generators will receive cleanly structured variables, avoiding generic, null-valued parameters that often crash systems later in production. Moving forward, we must address the challenge of text splitting. If we chunk text arbitrarily, we end up cutting mid-sentence, leading to loss of context for our embedding models. To prevent this, we use a recursive mechanism. This sequence diagram illustrates the step-by-step logic. The splitter starts with the largest separator, usually paragraph breaks, and splits further down to single spaces only if a chunk exceeds the maximum configuration size. By overlapping chunks, we preserve context at the boundaries. This ensures contiguous sentences remain whole, protecting semantic retrieval fidelity. Now, let's write the recursive splitting algorithm. In this code block, which you can also download via the link in the description, we write a clean splitter. Notice how we parse our document list, analyze the contents, extract partitions using clean string boundaries, and append an incremental chunk ID to the metadata dictionary. This metadata tracking enables us to trace any single vectorized chunk back to its precise parent document. Writing this logic yourself, instead of using bulky packages, keeps your deployment small, lightweight, and incredibly fast to execute. Let's examine the generated logs after we run our custom splitter on the output of our file loader. The terminal output confirms that our document was split into clean subsegments, and we successfully printed the exact text chunks along with their corresponding metadata dictionaries. Look at how chunk number 0 and chunk number 1 overlap cleanly. The end of chunk 0 naturally transitions into the beginning of chunk 1, keeping context intact. Each segment is carefully measured, showing the accurate character lengths. To truly appreciate why we append metadata to every chunk, consider a real-world library analogy. If you throw thousands of pages from different books onto a floor, retrieving information is chaotic, even if you read fast. Metadata acts like a catalog index, matching every single page to its book, chapter, page number, and topic. In RAG pipelines, we rely on these tags to filter search results by source, department, or update time, directly saving massive computing power during vector retrieval operations. By taking control of both your loading and chunking processes, you prevent garbage in, garbage out failures. Your data is now perfectly cleaned, partitioned, and enriched with structured metadata tags. In our upcoming session, we will see how these structured chunks are transformed into dense mathematical coordinates in space. Join me in the next lecture, Module 6.1, the Retrieval Process and KNN Algorithms, Theory, where I will explain how k-nearest neighbor math locates context in microseconds. Please check the link in the description to download the complete pipeline architecture and Python scripts. I'll see you in the next module.